So in the last video, we talked a little bit about just basic integrals, the ones that we already know pretty much just by looking at it what the antiderivative is going to be. But of course, very few integrals are exact fits for one of the formulas in the table of integrals that we looked at earlier. Just to look at that real fast, here's a basic table. So very few of these look like that. But what we often do is we do some sort of substitution. And so we have to substitute to get it to look like one of those in the table. Okay, and this technique of substitution was introduced in Calculus 1. It's in my playlist 5, Unit 5. And this technique is just the inverse of the chain rule for derivatives from Calculus 1. Chain rule could also be known as the substitution rule or the composition rule. So basic substitutions often allow us to work out antiderivative formulas. So after making the substitution, we obtain something that fits one of the forms in that table we just whizzed by a minute ago. So what we typically do is group together things that make up U, and of course replace it by U. And then we group together du, things that make du. Well, du is just a shorthand notation for du over dx, the derivative of u with respect to x, times the differential dx. And we replace all of that by du. Don't forget that we also have to take care of the relationship between dx and du. Oftentimes we're off a little bit. If we're only off by a constant factor, then the constant multiple rule allows us to take a constant factor out front of the integral sign. So if what we have differs from du by a constant factor, we can easily fix it by introducing the constant as part of du and placing its reciprocal constant factor out front of the integral. If there's a constant base with a more complicated variable power, then let's see if letting u be the power will work. So what we're working toward is b to the u and the exponential rule. So we're addressing this question, what do we let be u? Right? And so if we have a constant base and a more complicated power, let u be the complicated power. We're working toward the exponential rule. On the other hand, if we have a variable base to a constant power, let u be the more complicated base, trying for a power rule, u to the n. And if we have trig functions, often we can let u be the input for a trig function. And sometimes we just got to try stuff. Try some potential substitutions and see which one will succeed in turning problem into one that we can work out. Now sometimes these basic substitutions don't work, but this is going to be the first thing we're going to really try to do. So when you're working with a family of antiderivative problems, in other words, an indefinite integral, you will need to be sure to substitute back in your antiderivative, substitute back the value of u back into your antiderivative, so that answer will be in terms of the original variable. So you can't leave it in u's, you got to change it back to x's or whatever your original variable was. Now, if you're finding an exact value of a definite integral via the fundamental theorem of calculus, then there are basically two options. Option one is to indicate that the limits are x values, change the antiderivative back to a function of x at the end, and evaluate at the endpoint x values and subtract using the fundamental theorem of calculus. Option two is to change the limits to u values. And in option 2, you don't have to change back to x. You just plug in the values of u's at the endpoints and subtract. Either way is pretty close to the same difference. Probably option 2 is maybe a little better, but either one works pretty well. So here are several examples of integration problems using basic substitution. So here's the first one. Maybe I should let you look at these yourself. So here's one. Since these are really review problems, supposedly, let's look at the family of antiderivatives, or the indefinite integral of 1 over 1 plus 4x squared dx. So you might try to pause the video and see if you can work this out yourself. Well, that's not one of our basic functions, but we do have something that looks like 1 over 1 plus u squared we know how to do. So if you could just let let u be 2x, then the 4x squared becomes u squared. That does fit one of our patterns. But if the u is 2x, du is 2dx. Well, we got the dx, we don't have a 2. That's not a big deal. Just stick the 2 in here, put a 1/2 here, which we can bring out front. So if you sort of go backwards from this, you do see that this equals is valid here. Well, now with this substitution, this is 1 over 1 plus u squared, and then the 2x becomes du. The 2x becomes u, the 2dx becomes du. And you should recognize that from our table of integrals that we have memorized. That is the derivative of arctangent of u. So our antiderivative is 1/2 arctangent of u plus c, but of course we introduced the u. We need to go back and plug in the 2x in place of the u, and we see our antiderivative is 1/2 arctangent of 2x plus any constant. And here is a verification and a graph of that using the GeoGebra applet that we introduced in a previous video. Here I set these both at 0, so there's no shading for definite integrals, which of course makes the definite integral 0. But we do an antiderivative down here, and it gives us the same thing. Another way to write arctangent of 2x is tan superscript -1. That's not a power. That's an inverse tangent or arctangent function. I prefer arctan, really, but it's often written this way, including on a lot of calculators. So 1/2 arctangent of 2x plus some constant. Right now that constant is 0, and that's the green graph right there. The original graph is in blue. All right, here's another one. See if you can do this one yourself. A definite integral from 0 to 1 of e to the 4x dx. Go ahead and press pause. Come back whenever you have it done. Press pause now. Okay, I hope you worked this one out yourself, and now we can just check it. I'm going to show you sort of the two different options of how you can go at this. You'll see they're basically the same. So either way we go, we have the integral from 0 to 1 of e to the 4x dx. That's not one of our basic things, but we're trying to let u be the power 4x. We're looking for e to the u. So if u is 4x, du is 4dx. We can put a 4 here with the dx to make du if we balance it by putting a 1/4 out front. Now, if I just leave this 0 and 1 at this point, it is incorrect because you assume these numbers here are u values unless indicated otherwise. But it's okay if you go ahead and say these are x values by indicating x equals 0 to x equals 1, which indicates we're going to have to switch back to x in the end. So the antiderivative of e to the u is just e to the u. We want to evaluate from x equals 0 to 1. We have to get it back in terms of x first by plugging in the 4x. Now we can plug in x is 1 and x is 0 and evaluate. 4 times 1 is 4, so that's e to the 4th. 4 times 0 is 0, e to the 0 is 1. So our final exact answer is 1/4, parentheses, e to the 4th minus 1, close parentheses, or about 13.3995. Option 2 is basically the same thing. It starts out exactly the same. We let u is 4x, du is 4dx. And this time we let the 4dx be du. This is 1/4. This is e to the u. But this time I'm going to figure out what these numbers are in terms of u's. So if x is 0, I plug back in place of here. 4 times 0 is 0, so u is also 0. But when x is 1, I plug in here. I get u is 4. So we change this to 0 to 0 and 1 to 4. And now these are values of u. The advantage of this one is I do not have to switch back to x's. Once I get my antiderivative in terms of u, I can just plug these values in for u. Of course, the disadvantage is you do have to figure out what the u is when you change those here. So, it's about the same difference either way. Plug in the 4, plug in the 0, evaluate, and you're done. Okay, so again, the same answer either way. Here's an illustration of that as an area. So you take e to the 4x, which is this blue exponential function here. We integrate from 0 to 1. We're finding this green area right here. And there it is. See, the program gives it to you exactly. 1/4 e to the 4th minus 1/4. Same thing I had, except they distributed 1/4. And the same decimal approximation that I have as well. All right, how about another one for you to practice? The integral, definite integral, from 0 to 1 of 3x sine of pi x squared dx. See if you can do this one yourself. Press pause now. Well, when I see a trig function and it's got a input that's not just a single letter, I'm going to probably try to let u be that inside there. Something good to try anyway. So if we let u be the pi x squared, then du is 2 pi x dx. Okay, well, there's some good news here. I've got the x and the dx. If I just put a 2 in the pi and the x dx all together, that becomes du. But I can put the 2 here as long as I balance by putting a 1/2 out front. And I need the 1 over pi as well. So I need 1 over 2 pi out front. And then I can bring that 3 out front with it. So that makes 3 over 2 pi out here. So you might just check it at this point. If I take this and distribute in, the 2 pi's cancel. We've got the 3, the x, and then the sign of that pi x squared and the dx. This equals is valid. So that's good. Now, substituting in, pi x squared is just another name for u. 2 pi x dx altogether is just du. We still got our coefficient out front, but we now don't need to change these to u values. I'm using my second method that we just talked about. So here, if x is 0, I plug into here and I get u is 0. And if x is pi, x is 1, u is pi. So I plug that in there, and there's pi. So now I don't have to change to x's. When I find my antiderivative, which is the negative cosine of u, notice I brought the negative out front here, and I just evaluate from 0 to pi. So it's cosine of pi minus cosine of 0. Cosine of 0 is 1. Cosine of pi is -1. -1 minus 1 is -2. Cancels with that negative and that 2, leaving just the 3 over pi. So the exact answer is 3 over pi, and approximately 0.954929656, okay, a little under 1. And so 3 over pi is the exact answer given by the program as well, and there's the decimal, and there's the graph, and so it's all that green arrow. This particular function here is 0 at the origin, and then it goes up, and it comes back down, actually hits the axis again at 1. Okay, and so it's just this piece right here. It's that area, and it's, like I said, it's just under 1. I mean, you kind of should know it's a little under 1. 3 is just a little bit under pi, so that's a fraction just a little less than 1. All right, here's another one for you to try. The integral of x times parentheses 3x plus 2 to the 200th. Now, one way we could do this is expand this out to 201 terms, distribute the x, and do it that way. But that's the hard way. Is there a way to do this with the substitution? You try it. Come back and we'll check our work in just a second. Okay, now this one is a little trickier. You may have run into something here. So it's a little more advanced type of substitution, but it's still a basic substitution. So we want the base to be u. So that's the 3x plus 2. Okay, so I've written it right here. U is 3x plus 2. So then du is just going to be 3dx. Or in other words, dx is 1/3 du is another way to say that. So the dx is 1/3 du. That's no problem. This is u to the 200th, no problem. But the problem is we still got this extra x there. Well, since this formula right here for u is a linear formula, it's easy to solve for x. So if you get a formula that's real easy to solve for x right there, then this technique I'm using here might work for you. So solve this for x. So subtract 2 and then multiply by 1/3. X is 1/3 parentheses u minus 2. I take that and replace it by the x, this first x here. All right. Well, let's just see if that made anything better. Well, 1/3 times a 1/3 is 1/9, which I can bring out front. I'm going to distribute this u to the 200, so I have u to the 201 minus 2 times u to the 200. Oh, okay, that's a polynomial. That's easy enough to do. Power goes up 1 to 202, multiplied by the reciprocal, so you got 1 over 202 there. Power goes up 1 here to 201. Divide by that, you have -2 over 201. Of course, our integral sign's gone now, so we need a plus c. I could distribute the 1/9 here if I wanted to expand it, or I'd like to have it factored, well, this part of it factored here, then the plus c. So I'm going to factor out a 1 over 201 and a 1 over 202. to get rid of the denominator here. So it's sort of like getting a common denominator like this. So 202 times 201 times 9 is what gives you this bottom here, 365,418. So that's out front. And the smaller of the two powers is 201, so I can factor out a u to the 201. Well, what's left? Well, I factored out the 1 over 202. So basically what I'm doing is distributing a 201 and a 202 into this. And so that leaves me 201 here, and 202 times the negative 2 is negative 404 here. When I divide out by the u to the 201, that's gone, and there's just one u left there. So there's a way to kind of simplify that. Switching back in, u was 3x plus 2, so plug that in place of u here and here. I can distribute and combine like terms here to finish things up. 3 times 201 is 603, and that's times x. 2 times 201 is 402, minus 404 is 2. All right, so let's check this by hand without some technology, first of all. So first of all, I've got this coefficient out here that's going to come out front, and then I've got, of course, the derivative of c is 0. And then I'm going to use the product rule here. So it's the first times the derivative of the second. There it is, derivative of the second, 603. Plus the second, 603x minus 2 times the derivative of the first. The derivative of the first is 201 times 3x plus 2, and the power goes down to 200. And then you got to do the derivative of the base because the chain rule there, 3. Guaranteed we did a substitution. We're going to use the same substitution in the chain rule at some point in our check. Now let's see what we got. If it's 3 times 201 is 603, that's got a 603. So I'll factor that out. Okay, that's a 3 times the 201. Remember, this denominator was a 9 times 201 times 202. So we cancel one of the 3's and the 201. What's left should be just the 3 times the 202, which is 606 here. And they both have a 3x plus 2 to the 200, so I'm factoring that out. Now let's see what's left. That's gone. This is just one of these left, so that's first power. That term's gone altogether. That's gone. That's gone. The only thing left here is 603 minus 2. Combining like terms, that's 606x. The 2's cancel. Oh, look at that. The 606 cancels. We get x times 3x plus 2 to the 200th. Ah, good news, because that's what it's supposed to be. That's what we're looking for. So that one checks. Here's the calculator check. Remember how you do these. You put your answer in right here. It's running off the screen here, but that's my answer. And then down here in y2 is the numerical derivative of y1, math 8, excuse me. And then and y3 is the original problem. And the tables for y2 and y3 should check at least to a lot of digits. Now, this answer is actually correct, but the checks doesn't look like it's quite checking out here. It looks like there's a close. And the problem is because for this particular function, because how fast it's growing here, an h of 0.001 doesn't give you a symmetric difference quotient that's very good. The actual derivative is over here, or the actual original function's over here. The numerical derivative is here. We can actually go to mode on the calculator, put it in classic mode, or if you got a T83, just put in a smaller h there, and now the symmetric difference quotients are working out correctly. So actually it did check. So always see if a basic substitution will work before trying any of the more advanced techniques.